Now, I said on going to the next stage, they have to be, the mass balances have to be constrained, right? So I worked out this equation. This is the equation of the operating line, which is going to look something like this. The intercept over here is going to be xd over r plus 1. And the slope is r over r plus 1. See what I did? So I did mass balances only on the rectifying section. I worked out the slope of the line, and I just plotted that line on the same plot as the alpha equals 2. Now, for this given x of n minus 1, I now know where the mass balances have to work out. It has to be wherever this line intersects. So now I know I know which y is in equilibrium with this x. It's this y. And now I know where the mass balances fall for this line. It's this x. And I can continue stepping stages like that until I run into the pinch point.
So that's xd over r plus 1. Is that right? The point where...
This point is, it's the y-intercept. So if this x is set to 0,
Yeah.
this is the y-intercept. In practice, when you plot this line, what I do is I go to xd, because you usually know what xd is. And then you just draw a line of slope r over r plus 1. And then the intercept will be that point just by default. Okay, so you can do a similar thing for the stripping section. Or what's easy to do is if you know the thermal state of your feed, you can just draw a feed line. So for a saturated liquid, your feed line is just vertical. And for a saturated vapor, your feed line is horizontal. I think he has some equation in his notes, but if not, I wouldn't worry about it.
Horizontal.
So if you knew, I'm going to draw a new picture. If you knew what your feed composition is, which you almost always will, I just picked that z arbitrarily, and you knew the thermal state of the feed, which for a saturated liquid is straight up, you can draw a line like this, and then wherever it intersects would then be the intersection point of your stripping section line. So you can do a very similar thing for your stripping section and plot another line. That would look like that. So I'm not going to do the stripping section, but the only thing you have to remember is now that instead of V equals L plus D, you also have saturated liquid from your feed. So the stripping section would be this part. So it would be F plus L equals V plus B. Right? Yeah.
A plus B.
Could you explain that one?
This one?
Yeah.
Okay, if the feed is a saturated liquid, that is also coming in at this point. So it's entering the stripping section. So you have to count it as a liquid.
Okay.
So you can imagine it like if it's in steady state, the V's and the L's are all interchanging, and they're all equal to whatever's. So this V that's coming up from the reboiler will be the same V that's coming out here, but all the F, the saturated liquid, is just falling straight down. So there's more moles in this part of the column. So you just have to add that F. So if you do a similar kind of thing, like I said, you can plot a line that looks like this. And then if your feed is optimally located, which is another word to watch out for, that means that when you're stepping your stages, you step once your stage line steps over this intersection line, then you switch over to the other operating line.
What's the keyword for that?
If the feed is optimally located. Or the feed is in the best place or something like that.
Would that be on 3 or 2 or 1? Do you count from the bottom up or?
It doesn't matter, whichever, just as long as you're consistent. I think the convention is actually you count from bottom to top.
Yeah.
So you take
So
the
3, 2, 1, reboiler.
So that would be 1 on that one?
Yes.
I got a question. If you do that back to the graph, when you graph that point, that second line,
This guy.
yeah, where
Okay.
do you get that point from? The bottom right there.
Oh, that's your XB. You can figure that out, or that'll be given, or you might have to guess that. But somehow you'd know that that's your XB, and then you have to.
So for the optimal feed, you basically you look at the lines, whichever one goes, whichever one it like goes closer to the endpoint or whatever.
All right, hold on. So first, this is the reboiler, stage 1, stage 2, stage 3. So when I was stepping, you step on the rectifying section line until you cross your turning point.
Okay.
And then I started stepping on the stripping section line.
Okay.
Now, say my feed was not optimally located. Say I've specified that I have to have 5 stages on the top and 1 stage on the bottom or something like that. Or say it's a 7-stage column and I'm feeding into stage 1. Yeah, let's say that. Let's say 5 stages. The feed is on stage 1. So now I have to do.
Do they have to cross right there? What if they don't? What if they don't cross?
They will always. The 3 lines will always intersect at the same point because of the constraints of mass balances.
Okay.
That's kind of like where the feed line comes in. So the feed line isn't an actual thing. It just tells you where the intersection point is. So what do I need? I have an R, a 1, 2, 3, 4, and a 5. So that means I have to do 4 stages until I cross over. So that's 1, 2, 3, 4, 5 over. Did I do that right? R, 2, 3. Yeah. So now notice that I have more stages, but I still get the same separation because the stages that were in here are not as efficient. I wasn't getting as big as a step because my feed was not in the best place for this type of column.
So, looking at this one, this would be considered 2 phases, 4 phases, and you feed in at phase 2?
Stages.
4
So,
stages.
yeah. Careful with that because that phases could imply that.
Yeah, in this stage. I'm saying that's 4 phases, 4 stages, and we feed in at stage.
So the reboiler doesn't
Six
count as a
stages, yeah.
stage, but it is in equilibrium, so you have to count it.
And we would consider feeding in here at about 2?
Yes. Yeah. Was there an
Why is that feed stage on the optimal feed?
It's stage 1.
Okay.
Yep.
So the one you do on the right is an
Correct.
Can you explain what's going on in each of those, not tile lines, but each of those lines? So what's going on with 1, 2, 3, 4, 5?
So you're doing this graphically. You know what your XD is. That has to be in equilibrium with the stage below. That stage has to be in mass balance. That has to be in equilibrium with the stage below. That has to be in mass balance.
So you basically have like the steps, kind of. You have what's going in, and what's going out.
Right. It's just a graphical way to solve a lot of equations very quickly.
Okay.
Yeah.
BJ, can you differentiate both of these graphs as to how optimal versus not optimal are different from each other?
So this one you need more stages to do the same separation because in this region I haven't stepped over to the stripping section line. So like this guy and this guy are both stepped on the rectifying section line as opposed to
you
on
haven't gone down once you pass
Yes.
the intersection.
Yes. So
Oh.
this is what you're looking at, and then this is what you're looking at as opposed to going over there.
Okay, so you wouldn't do that if you were, so you would do the right graph if you were told that the
Yes.
distillation column is not optimal.
Correct.
Okay.
Good till now. All right, now I'll talk about the limiting cases. What should I erase?
Did you say if we're told nothing about the feed placement, should we assume it's optimal or?
Yeah, you'll be told something.
Okay.
Or you might be asked to find the optimal feed stage.
Okay.
Like there'll be hints.
Can I take a picture before you?
Yep.
Okay, so you said we have to count the reboiler because it's in equilibrium. Does that mean that if we had a partial condenser, we would have to count it also?
Yes. That's Kevon, I was getting to that. So you mentioned what that would look like if it's a partial condenser. It would look exactly the same. So in the case of a partial condenser, you would have another stage. Or like in this arbitrary example, this would be the condenser because the reboiler is in equilibrium. So it would still look like this. This would just be the condenser stage, not the top stage.
But we would still count it as the number of stages that it.
Yeah, you count the stages and then the reboiler and the condenser separate.
Oh.
Hopefully there will be another.
So when you're working out how much one of these distillation columns is going to cost, the two main variables you look at is what are the number of stages and what's your reflux ratio. And those happen to be, there's an opposite relationship. So the more number of stages you have, the purer your product is, the less reflux you need. And then the reverse is also the same. So in total reflux, L over D tends to infinity, which means that R over R plus 1 tends to 1. And in that case, your reflux line is equal to the 45-degree line.
Could you say that last thing over there?
Your operating line is equal to the 45-degree line. So if I want to separate something between XD and XB, all I have to do is simply step stages off the 45-degree line. And in this case, it doesn't matter what the thermal state of my feed is because it's infinite reflux. And there's
What's a total reflux? Where is that in the picture?
In what picture?
That?
Total reflux would be, there's no D, it's all L.
Oh. Okay.
So if you get, if D is like 0.0001 moles per hour, and L is 30 moles per hour. So this is obviously the minimum number of stages because you get the most separation from each stage. I say separation, but it's separation.
Like separation.
Separation.
Yeah.
How can you have an XG if there is no D?
You can make the idealization that it's very, very small. Just say it's
Like L over D transform.
same thing that we did before. We just say it's very, very small, but there's like one drop. So this at least gets you somewhere. This tells you can't, if you have specifications of an XB and an XD for a given Z, you can never do it with a Rayleigh still or a single stage thing, or even a two-stage thing. That tells you have to have at least 3 stages. So in the other limiting cases where you have an infinite number of stages, that's going to look ridiculous because your column is going to be very tall. But the minimum reflux ratio, so you'll have a given Z. For this one, you do need to know the thermal state of the feed, so we'll keep with the saturated liquid example. This out. So remember, your reflux line is curving. The absolute minimum you have to have corresponds to where the feed line intersects the equilibrium line. So if I had a slope that looked like that, if I had very little reflux, and my reflux line slope tended to 0, I could draw as many stages as I want up here, but every stage would not give me any more separation because the reflux is so small. So even if I had an infinite number of stages, I could never get to past this pinch point.
So you need to go past that pinch point to get to the.
Yeah, you have to get to XB somehow.
Okay.
So, what? I lost you. I don't know what just happened.
Okay, the reflux, the operating line is a line that comes from this point. That can have any slope you want,
Yeah.
between 0 and 1. So if I pick a reflux ratio that's very, very small, so L over D tends to 0 now, instead of infinity, that means D is very large.
Mhm.
That means my slope, R over R plus 1, tends to 0.
It's almost a straight line.
Yeah.
If it's horizontal like this, then as I add stages, I just keep stepping against this line, and I'm still stepping infinitely small, and I keep doing that
What if your
in
feed line
perpetuity.
was-
Huh?
What if your feed line was further out? Like,
Well, yeah. So it's obviously so if I move my feed line out here, then your minimum reflux line it's gonna vary. So that was just an example. So for this, my minimum reflux is the line that intersects my feed line.
That's the minimum.
Yes.
Always.
So whatever the slope of this line is, that gives you your minimum reflux ratio.
Oh, okay.
So now as I step, I still have an infinite number of stages, but at least I reach the pinch point eventually.
And now the other one's R max. When it's 40.
Well, yeah, but R max is like infinite for total reflux. So this also tells you something, that you can't go less than R min because you'll never get to your product. So after that, you can design from there. I think that